So today I think we have only 2 sessions, right? Okay, so most likely we'll finish this section on conservation equations today. So yesterday, last session or the third session, we were doing the conservation equations, and so we discussed the mixture conservation, or I should say the mixture mass conservation, and then the species mass conservation. Okay. So this is the equation we were discussing at the end. So again, to re-emphasize, so you have the rate of change of mass for species I, when you consider any species, right, I. Then for one-dimensional case, you get this ddx of this mass flux, okay, and this mass flux is due to convection and diffusion, okay. So this mass flux of species I, as indicated there, rho I. So in the vector form, then this is a vector. So density of species I, the mixture velocity, then rho I VDI. And this rho I VDI we write as minus rho di m and then the gradient of yi, right? So since this is a vector, so this quantity in the x direction will be rho I ux, correct? So this will be just the u component of v. And then here we'll get rho I dim, and the x component of this will be dy dx. Okay. So this way you can write for one-dimensional, two-dimensional, or in the vector form for 3 dimensions. And also we discussed yesterday that we are taking a small control volume inside the reacting flow, in the flame. Okay, so where you have all gradients. There are gradients in velocity, species mass, everything, right? So then this quantity is defined here at this phase. Then on this one, it will be mxi plus ddx of mxi. Double prime. And then the net, so what we are writing is di dt times the volume is equal to the mass flowing in minus mass flowing out. So this minus this. So that's why we get ddx of mxi double dot. And then the volume. And the last term, that's the source term due to chemical reaction. And I think the best way to write is what we are more familiar with this Wi dot times the molecular weight of species I. And then you can write this in the one-dimensional, or for example, let's say if you have axisymmetric flow. Like if you have a jet flame, then you have z and r coordinates. So if you have a jet flame, let's call this x and this is r. So then you write 2-dimensional equations, right? Axisymmetric 2-dimensional. So then the 2-dimensional form of this equation will be, so rho I you write as rho yi dt Then on the right hand side, you'll have minus. So now we write it using this form. Okay. So let me just write the vector form first, and then we write the for the jet flame. So this is divergence of that vector, which is rho I vector v minus rho di, and then the gradient of yi, correct? And now we can write it for the x and r coordinate, x and the radial coordinate, and of course you have the source term, which is does not depend on the coordinates. So this one now you can write as minus ddx of rho I ux. Rho I you can convert to rho times yi. Okay. And then the radial part, so that will be the two convective terms, okay, corresponding to this quantity. Okay. And then the diffusion part. So that will become plus ddx of rho di dvi dx plus 1 over r ddr r rho di dy dr. Okay. So that's the purpose of writing this in the vector form, because then you can apply to any any flame, any coordinate system. So same way we'll do for the other equations. Okay. All right. Any questions? So we discussed this material. So we'll go to the momentum equation today, momentum conservation equation. So erase this part. So momentum conservation, we all know that is based on the Newton's second law. Okay. Or you can use the same idea, we are using the rate of change of momentum, right? What is the rate of change of momentum? That's due to the mass, the momentum flowing in minus momentum flowing out, okay? And what are the rest? The forces acting on the control volume, okay? So you use, you know, that approach. So the rate of change of momentum. So for the time being, let's consider only momentum in the x direction, ux, okay? So then what is the rate of change of momentum? ddt, okay. Rho is the mass, right, mixture mass. So this becomes the momentum per unit volume, okay. And then of course we multiply with the volume. So this is the rate of change of momentum. This is now momentum flowing into the control volume minus flowing out of the control volume, right? Okay. So that will be again, we will write the momentum flow rate here. It will be rho ux, that's the mass flow rate per unit area. That becomes the momentum flow rate per unit area, okay. And then we can write the same quantity here. So when you take the net, it will give us rho ux times the volume, okay. Will be this minus this quantity right. So the net will be minus this quantity, Okay, what else? Now, if it is, okay, then there is a mass flow in this direction also, correct? So, that mass flow is rho uy. Okay. Now, since we are considering a flow like this, so the flow has, two components or three components depending on the case, right? So, there is a momentum here in the x direction also. Okay. So, if you can consider this, that will be minus d dy rho uy. I think here I am mainly using Vx Vy, that does not matter. So, we'll change it later on. Okay. So, this is the net rate of change of ux momentum due to the flow in the y direction. Okay. And then, of course, you can add the z direction also, okay, same way. So, that is the rate of change of momentum due to convection, due to the flow. Okay. And now we consider the forces. So, what are the forces we consider? Okay. Body forces, yeah. What else? Yeah, the viscous forces we should call, and pressure forces. Okay. So, we will consider these forces, and basically what we get is the Navier-Stokes equations, right. So, now any given surface, let me make a little bit of a three-dimensional volume. So, why not make it a little bigger so that we can show all the arrows. So, now the pressure forces first. Pressure is the easiest one to deal with. So, you have P force here, so that will be P times dy dz, okay, on this face. Whereas on this one it will be P plus dp dx and dx. Okay. So, when you take the net, you will again get minus dp dx, okay, times the volume. Okay. So, that is the pressure force. Okay. In general, the pressure force is always minus del P, that is the vector. So, this is the pressure force per unit volume, and then you can take components. In the x direction it will be dp dx, y direction dp dy, so on. Okay. So, that is now the viscous forces. Now, viscous forces is a little more complicated, because if you consider any surface like this surface, you have the normal viscous stresses. Okay. So, this will be, so now I use the convention, I use two subscripts. So, that is also a normal way of writing sigma xx, or rather sigma yy here. Okay. So, two subscripts. Okay. So, what does this mean? The first one is the area. Okay. So, this is the y area of the top area, okay, because the perpendicular to this area is in the y direction. So, this is the y area, and this is the direction of the stress. Okay. So, this is one, and then you have the viscous stresses. So, one will be this direction, other one will be this direction. So, this one will be, no, the area is same. So, all three will be sigma y, sigma y, sigma y. Okay. This will be sigma yx, this will be sigma yz. Okay. So, that is how you write this now. Look at what are the forces due to viscous stresses which are acting in the x direction, right. So, you have first of all sigma xx, and it is the direction is opposite of the pressure force. So this will give us ddx of sigma xx. I think I'll just skip writing volume all the time because there's no need to write volume everywhere because we divide by the volume. So that's the viscous force, the normal viscous force, okay, in the x direction. And then you have the shear forces. So one will be sigma y or ddy of sigma yx, okay. And if it is three-dimensional, you can add the third one, okay. That will be, of course, I will just write the two-dimensional case, but just for completeness. Actually, I'm supposed to take the phone out, right? But it looks like it's okay. Right, so keep the phone or Ankit's? Or maybe I'll just leave it here. Sorry. That reminder. Okay. So you can add the third one. This will be sigma zx. Okay. So you got the normal stresses, viscous stresses, okay, and the pressure forces. So forces due to pressure and then the viscous stresses. Okay. And then gravity, of course, you just add because that's a body force. Okay. So I'll just say Fx. You can always write the expression for Fx. Okay. So that's the x momentum equation. Okay. Now here I have written also in the vector form. So this is the form which is like three-dimensional. Okay, here I means I could be x, y, and z, three directions. Okay, so that's a very convenient way of writing. Okay. So I usually prefer this form because then you know it's also three-dimensional, and also it's also easy to write all the three momentum equations from here because just take, you can take either I 1, 2, and 3, or you can take x, y, and z. Okay. But then be careful with this j. So for example here, if I write the x momentum equation, I can say I equal to 1 is the x momentum. Okay. So then if I focus on this equation, it's ddt of rho v1. So now v1 is the velocity in the x direction. Okay. And these terms are written on the left-hand side. So this j here, and this j means you write three terms. Okay. When you see same index, same subscript appearing, you know, in the equation twice, that indicates the sum. Okay. So this will be ddx1 rho v1 v1 plus ddx2 rho v2 v1. Okay. So the equation is for v1. Okay. So vi here xi, which will be dp dx1, and same way this viscous stresses. And the third one is ddx3 rho v3 v1. Okay. And then dp dxi will be dp dx1. And then the viscous stresses you write the same way. Okay, I'm using tau there, not sigma. So you can choose whichever you like. Tau 1 1 x1, correct? And then the next term will be now, okay, it will be 2 1 2. So 2 1 dx2. And that way you write the third term. Okay. So that's for the x momentum equation. Okay. Similarly, you can write for the y, you take I equal to 2 now. Okay. So the j index is really, okay, you can use anything there. You don't have to use j, you can use L. Okay, because all three terms you have to write. Okay. So this is called the conservation form of the equation. This is called the non-conservation form. So this is just a convention, and you can get this form from the conservation form. Okay. And both are used depending upon the case. Usually when you do CFD, they use this form. Okay. Analysis, a lot of times we use the non-conservation form. Okay. So when you use finite volume methods or other methods for solving the equation numerically, this is more commonly used, the conservation form. So let me get the non-conservation form, and then you can see the difference. Are you familiar with the conservation and non-conservation? The two different forms. Yeah, go ahead.
For deriving the non-conservation, we assume the fluid particles to be moving.
Oh, well, we are using now, okay, not the Lagrangian approach, the Eulerian approach, okay, in both the forms. Yeah, you can say, if you derive directly, then we are using, the Lagrangian form for the fluid particle. Like, what is the acceleration of the fluid? Okay. Yeah, you're right, that sense, because what is the acceleration of the fluid? Or the forces on the fluid, mass times the acceleration, right? So what is the mass? Mass is rho. Okay. And the acceleration is written as dvi dt plus vj dvi dxj. This is the acceleration term, what you call the total derivative or the substantial derivative, okay, for a moving particle. Okay. Because acceleration, this is at any position, if the flow is unsteady, this is due to the flow, acceleration. Okay. Yeah, you're right, in that sense we say for a moving particle. Okay. But here, we can get it directly from this equation. Okay. Yeah, so this is another way people discuss this or derived it. Mass times acceleration equal to forces. Okay. Now, to get this form from the conservation form of the equation, you can just split the terms. So the first term will be rho times dvi dt, correct? And then we will have the other term, which will be vi d rho dt. Okay. So that's the first term there. Okay. Same way you can split these terms. So this one is rho vi dvj dxj, and then vj rho, or not rho, rho dvi dxj. Okay. So the second term also you can split into two terms. Okay. Did I write correctly? Rho vi dvj dxj, and then no, there is something wrong. Which one we correct? So let's write this again. So let me write it here. Okay. So just take vi out, then it is ddxj rho vj. Okay. And then the next term is rho vj dvi dxj. Yeah, this is correct. Okay. So now this term and this term appear in the non-conservation form. Okay. So what about the other two terms? Okay. If you look at the terms, is vi times d rho dt plus Okay. Now, recall that this is the from the what is the mixture mass conservation equation. Okay. So if you look at the mixture mass conservation equation, we can go back here. It's not working today. Low battery. Okay, just check that I can use directly. Sorry? No, वो slide में. Oh, it moved, yeah.
इसका भी प्रॉब्लम सर आप पॉइंटर यूज़ कर सकते हैं
अच्छा, क्या यूज़ कर सकते हैं? Yeah, pointer I can use, yeah. Okay. Okay, here is the mixture. So this equation, so if you write in the same form, this is d rho dt, and what is this? d dxj of rho vj. Okay. So this quantity, these two terms inside, is 0. Okay. So this is like the net rate of change of mass times Vi is 0. Okay. So that gives us the non-conservation form. Okay.
Sir,
Yeah.
what is the physical significance of this conservation form and non-conservation?
No, these are two different ways of writing. You know, when they use CFD, so we use like finite volume approach to discretize the differential equations. So if you use the conservation form, then they make sure that the momentum is conserved. There's no extra source of appearing due to numerical method. Okay, so there it is meaningful. Okay, and we are considering the conservation of momentum. Okay, so then conservation of momentum, this is like the natural form because we are considering the rate of change of momentum due to the, just like the conservation of energy or species. Okay. Whereas this form we are saying, okay, the mass times the acceleration. Okay. Okay, the next thing then now is how do you write the stress components? Okay. So total there are 9 components, right? Because there are 3 surfaces, 3 faces. So each face there are 3, 1 normal, 2 shear. Okay. So if you use the assumption of Newtonian fluid, okay, and then the stresses are linearly proportional to the strain rates. So without going into those details, so this is the what you call the stress tensor, all the 9 components. Okay. Now what happens, there are actually only 6 unknowns because 3 are same. Okay. So if you write this, using the what you have here, tau 1, tau 1, 2, and so on, so you can write those. So let's write 1 or 2 of these. So for example, x momentum equation, you have tau 1, tau x1, tau 2, tau 2, 1, dx2, and the third term. So what is tau 1? The normal viscous stress in the x direction. So that will be, using that equation, it will be 2 times dv1 dx1, because now I is equal to 1 and j equal to 1. Okay. And then the next term 2 over 3 mu Okay. This is the divergence of velocity, okay, vector. So this, of course, you just write as it is. Now, if you recall, if you consider incompressible flow, then this part is 0. So otherwise, this is the full expression for Newtonian fluids. Similarly, you can write the shear. For example, see here we have tau 2(1). So tau 2(1) will be the viscosity, dV1 dx2, dV2 dx1. Okay. And then this one is same, it doesn't change. Okay. So this will appear, this term will appear in, okay, all 9 components. I'm feeling there may be some kind of a typo here. I will double check. Yeah. Yeah, that's what I just realized. That's what I'm thinking, that there is a typo. Yeah, this does not appear in the shears. Okay, this is only in the normal. Okay, because this is at the compressibility. Okay, so compressibility means this fluid can expand or contract. Okay, so that's only due to the normal components. Okay, not shear. Okay, so what is missing here is we put this Kronecker delta Ij in front of this term. That is missing here. That's the typo. So you can make a note of that. What it means is if I is equal to j, then this is 1, otherwise it is 0. Okay. Yeah, you are right. That was what's missing. Okay. Okay. So those are the, and you will see that this one, tau 2(1) is equal to tau 1(2). It will be same. Okay. So there are only 6 equations. That way. And here I written for convenience, for 2-dimensional x and y. So just to emphasize, there are different forms of the momentum equation depending upon, what flow you are considering. Any questions? Okay. So now we go to the energy equation. Energy equation is probably the most, complex to derive. When you consider all the effects. Okay. Did I skip already? It went so fast. Yeah, here. Energy equation. Okay. Okay, so first look at the more general form. Okay, what does it mean physically? So we consider the energy now per unit mass is kinetic energy, the internal energy and the kinetic energy. Because now we have flows, reacting flow. So you have of course, the internal energy, which here I am using is U for the internal energy, and then kinetic energy per unit mass, V square over 2. So we will consider the conservation of this quantity E. Okay. And then of course, the total energy will be E times the mass, which is rho times V. Okay. So the rate of change of energy, so then you have the rate of energy flowing in minus the energy flowing out. Okay. and then the source terms. Okay. The source terms will be, you have different forces now, right? You have the pressure force, viscous force, and the body force, gravity force. So the work done by these forces will be represent the source terms. Okay. So that's the basic idea, that rate of change of energy is due to the change due to the flow, and then due to the work done by the forces. Okay. Now remember, the basic equation comes from the first law of thermodynamics, so we should not forget that part. There are a lot of terms, but basic principle is the same. The change in energy is delta Q minus delta W. That's the basic form. Okay. So let's look at now, okay, what contributes to this Pi in, Pi out. Okay. So Pi in, there are three terms. Okay. So this is the heat flux vector. Okay. So you have three components here. What is this one? This one we are all familiar with. That's the conduction. Okay. So it's written in the vector form. So the thermal conductivity times the gradient of temperature. So it will have again three components. The radiation, okay, we don't have time in this course to study in detail any, the radiation, because there are many different models for radiation. Okay. So many times we used a very simple model which gives like the radiation term will be like, proportional to temperature to the power 4. Okay. But there are more sophisticated models, and depending on what you are studying, people use different models for the radiation effect. So we will not spend too much time on this one. So other than that, we have conduction. So let's look at this term. What is this term? Okay. This is the heat flux due to the species flux, because as this species, what is the species flux? So species means species I, diffusion flux. This is rho I VDI, correct? Okay. So that's what you'll see inside there. So as this flux, this species is flowing due to the, what is the mechanism? The gradient in the species concentration, species mole fraction, right? Because we write this as minus rho di delta yi, right? So this is due to the species gradient. So when there is a species gradient, there is a species flux, diffusion flux, and this will also give you the enthalpy flux or the heat flux. Okay. Because the species are flowing due to diffusion mechanism, enthalpy flux. So that's what this term is. And then of course you sum over all the species. Okay. Also there is a side point here, that if you just consider this quantity, this is the mass flux of species I due to diffusion, correct? So if you sum this, what do you get? Okay. Sum of this is 0. Okay. There is no net movement of mixture due to the diffusion. Okay. Some species are diffusing in one direction, others are diffusing in the other direction. Okay. So this is net is 0, but this is not 0, because each diffusion you are multiplying by HI. Okay. So in addition to conduction, you have another term which is the heat flux due to species diffusion or enthalpy flux. Okay. So now we can write the first part of the first term here, Pi in, Pi out. Okay. So that's very simple. This is similar to the mass flux. Here you have Pi in. Here you will have P plus dP dx dx. Okay. So P here is now Q vector So I don't have to use P at all. So this will be Q plus dq dx dx. Okay. So when you start writing now, you'll get d dt of rho, and then E, remember E is u plus v square over 2. Okay. And then on the right hand side you'll have dqx delta q delta x, right? Partial derivative of q with respect to x. So that's those two terms. Okay, pi in minus pi. Now the more complex is, okay, the work done due to forces. Okay. So remember now that going back to the original equation, first law. Okay, what was the first law? Change in energy is Q minus W, right? So this is the Q part. Okay. Now we are considering the work done, rate of work done. Okay. So we'll again consider one at a time. Let's go to the next slide. Oh, okay, it's not moving, I forgot. Okay. Oh, wait a minute, I forgot the convection part. Sorry, I forgot the convection part, the big part. So P has, so this is the, so this Q is only conduction. I'm using lambda, right? Lambda. So in the x direction it is lambda dt dx, and then you have the diffusion part rho I vdi hi. So that is Q plus the radiation term. Okay. Now for our discussion we will not include radiation in the disc. We can always add that radiation, okay, if needed or when needed. Okay. What I forgot here is this E energy times the mass flux, rho ux times E. That's the energy flux, okay, due to the convection. Okay. So this you can add here as minus ddx of rho uxe. Okay. And here I make distinction, should make distinction, this is just x component of q. Okay, dqx dx. And now we write this source term. Okay, so for source term we consider the work done by the forces. So we'll just consider just the work done by pressure, and then we'll take a break. Or just consider, okay, how do you write the equation for the rate of work done? Okay. So from basic physics we know what is the work done? Force times distance, right? So it's force times distance. So to make the rate of work done, it becomes force times velocity. Okay. So we take the force vector and then take the scalar product of the force vector with the velocity vector. That gives the rate of work done. Okay. So this is the basic physics we are using to write the rate of work. So if you consider it this way, here you have pressure P, here you have P plus, actually I will write this in a minute. So P, okay, then the velocity will be, of course the velocity here is, let's say, 3-dimensional. But when you take the scalar product, it's only the x component of the velocity which is important, right? So it will be P times ux, okay? And on this side it will be pux, okay? So the net you'll get will be Pux. Okay. So here I only written the three-dimensional form. So let's write some of these components. Okay. So this is one of the terms for the pressure work done. Okay. Now for the other velocities, this will be on this face. So this is P, but the velocity now will be Uy. Okay. So this will give us ddy of Puy and then minus ddz of Puz. Okay. So for pressure work, you get three terms. And also remember that the energy equation is a scalar equation. So you have to add all the terms. Okay. So now the viscous and the shear we'll discuss after the break.